This is the IBM Quantum Platform dashboard. On the first tile you can see what plan you're on, the monthly usage and time remaining for that plan, 10 minutes free per month on the free plan, any jobs you have in the queue. You can upgrade your plan from the 10 minutes free per month to pay as you go for $1.60 per second. Any quantum instances and classical computer simulators you have on your plan. Documentation for utilizing Qiskit, the language of IBM Quantum. Learning section for using quantum computing in general, Qiskit. The IBM Quantum Composer for building circuits. The Quantum Lab for using a Jupyter environment. And news on the right hand side. The next tab on the dashboard shows the compute available. First page shows the quantum resources and simulators available on your plan. First, the quantum is listed and the simulators underneath of it. We take a look at all the systems available on the quantum platform. First one listed is an exploratory instance with qubits, error, and speed listed in that order. Exploratory instances have to be utilized underneath of a premium plan. A little bit slower than what's available on the free and paid plans, but the error is lower. The speed is similar to the paid and free plans, but if you need more than 10 minutes per month, then the paid plans are unavoidable. This CLOPS H takes into account the hardware layer, as more physical gates can be run than virtual. CLOPS V only takes into account the virtual layered gates. And the simulators tab to view all the simulators available. And on the jobs tab, you can see the jobs you have in the queue, time used, remaining, jobs completed, details about the usage. On the dashboard, underneath the learning section, you can use the IBM Quantum Lab to build quantum circuits in a Jupyter notebook running Qiskit, or you can use the IBM Quantum Composer to build circuits graphically, remain impartial to any programming language. These two tabs in the Composer lead to tutorials. The lab link leads to a Jupyter notebook. In the Composer, you can edit the title of your circuit, perform basic file operations. Underneath Edit is where you manage the registers. You can add quantum registers, which hold qubits, name those registers, add or remove qubits. You can also add classical registers, which hold results from the qubit operations and allow you to reuse those results. You can also add qubits directly to the circuit by clicking on one of the qubits, pressing the plus sign. You can also add bits to the classical register by doing the same. You can add entire registers to the circuit. number on the right is the number of bits in that classical register. C0 is the name of that classical register. Underneath the view section, you can adjust the appearance of the circuit in various ways. With alignment, you can adjust how the quantum gates are laid out on the circuit. With left alignment, the gates snap to a leftmost position sequentially. With freeform alignment, the gates can be placed in any column on the circuit. The circles at the end of each qubit circuit are called the phase disks. They represent the qubit state in a purely Bloch-sphere perspective. That is, with the Z gate on the first qubit here, you can see that the phase is represented as 0. That is because on the Bloch-sphere, you wouldn't be able to tell the difference between a 1 state that has had a Z operation or hasn't. It only sees the same phase, and so it's represented that way with the phase disk. The probability of the 1 state is represented with how much shading of blue is in the phase disk. Here, with a 100% probability, the disk is fully shaded blue. Towards the bottom of the page is a Q-sphere representation for the combined state of the qubits. Each possible string of qubits is represented as a point on the Q-sphere. Each point is placed vertically on the sphere based on the number of zeros in the possible string. Possible states with more zeros are placed at a higher position on the sphere. Only the height of the point has meaning on the Q-sphere. Though the phase in the first qubit, qubit 0, is global, its value is maintained on the Q-sphere, just as all the additive phase in each possible string. This additive phase does not play a part in qubit operations. Here, after the NOT operation on the 0 state, a Z operation on the 1 state would produce an amplitude of -1, or a phase of pi. The color on the wheel next to the Q-sphere also matches the phase to the point on the sphere. With 2 of the 4 qubits in a 0 state, the point on the Q-sphere is halfway up. The additive phase remains the same. On the left, there are probabilities for each possible state. This view can be switched to another bar graph with amplitudes for each possible string, with color-coded phases that match the Q-sphere. Scrolling down, there's a state vector with complex amplitudes for each possible string. On the far left-hand side of the page is a link to the files, as well as any jobs in the queue running on instances or simulators, as well as documentation for building circuits. You can't click off this page, you just click the panel once more to exit out. You can right-click on any of the gates to obtain information about it. This is the controlled NOT gate. The controlled NOT gate acts on a pair of qubits, with one acting as the control, the other as the target. If the control is in a 1 state, then a NOT operation is performed on the target. Here, blue is used to represent the one state. Looking at another gate, the CC NOT gate, also known as the double controlled NOT gate, has two controls and one target. When both controls are in a one state, a NOT operation is performed on the target. Here the one state is represented with blue, the zero state with yellow. As one of the qubits is in the zero state, no operation is performed. Taking a look at another gate, the swap gate. The swap gate swaps the states of two qubits. Performing a NOT gate on the first qubit, the phase disk becomes fully shaded blue, probability 100% for the one state, while the other disks remain unshaded. Looking at the Q sphere, has 3/4 height. In the probability graph, you see full probability for the string with 1 in the final position. Adding a C NOT gate with the control as the first qubit, target is the second. As the first qubit is in the one state, the second qubit is moved to the one state. Adding a CC NOT gate with the first and second qubit as controls, the third qubit as a target, they just move to a one state. Now with 3 ones and 1 0, it is at 1/4 height, and the string for 0 1 1 1 has a probability of 100%. The state vector doesn't show any new color, as there is no phase on the only available string. Adding some phase, an S gate, which is equivalent to half of a Z gate. It adds a phase of pi/2. The color is represented on the Q sphere as well. Phase disk still shows no phase, as this is on a one state and can't be seen differently on a Bloch sphere. You can edit the properties of a gate by left-clicking on it, clicking the Edit button. The control for the CC NOT gate is the first and second qubit. the target as the third qubit, updating the target to the fourth qubit, the probability for the third qubit in the one state has dropped to 0. And the amplitude is updated with a 0 in the third qubit's position. Performing a measurement on the first qubit, having it written to the first position of the classical register. Amplitudes have not changed. Neither has the Q-sphere. However, the probability graph has changed. As the classical register is being used, it is now what is reflected in the probability graph. The number next to the arrow represents the position in the classical register that the result is written to. Measuring the fourth qubit, having it written to the fourth position in the register. See, the probability has been updated. Changing that measurement to the third qubit, but leaving its written result to the fourth bit in the classical register. It contributes a 0, leaving the string, the probability graph, with 1 in the final position. We can edit the measurement to have it reflect the same qubit that it's measuring, writing the result to the third position.